All right, let's do the S-gate challenge. So we want to be in the 1-1 state with gold. How we go about that? Of course, both qubits have to be flipped. And remember the rule, green with red make gold. In this case, where on the left, on the right qubit, we have one, we have just red. In the case where just one, on the leftmost qubit, we have just green. But in the case where both qubits are on, we're gonna have gold. And when both qubits are closed, we have the same blue. 3 qubits, nothing special. Doesn't matter where we add these, the colors will look different. But again, what we care is the last state, and we always know that the last state is always the addition of all the colors, no matter where they're placed, from all 3 qubits. Because why? Because all 3 qubits on the last state in the Hilbert space will be in the 1 state. Okay, now this is again a situation in which we don't need to do then nothing more than simply make sure we flip one of these qubits like that. Yeah, or again, to teach you a different rule, you can just do something like that. Yeah, this again wouldn't matter. As I said, if the qubits are on, you can even do it, go a bit deeper and do something like this. Yeah, you always think of all the colors of the qubits that are on, and the moment you understand the qubits are on, then you simply have to move the directions. So all the colors for all the qubits being on, they add together and they create this thing on the rightmost state that will give you exactly the addition of all the colors. Okay, this looks a bit tricky, right? But it's not really, because if you look, we still have row here. There's a bunch of different ways we can do that. So we can pick up green by just placing this here. We'll pick this green, and this green with the other green will make red. Then we just close the red and flip again here, right? But there are so many other ways to do it. So it's up to you. Yeah, I'm flipping in the wrong place. This cannot work apparently because this needs to be 1. So if it needs to be 1, we have to make sure it is 1. And then, okay, so this doesn't need to be here. Nothing needs to be there. We simply have to kill the color, and that's it. This is, I think, the most efficient solution we have here. Maybe picking up one of the the qubit 1 and something like that, you can find a more efficient solution. All right, so again, this shows the fact on how the colors actually change everything. And if you want to go really deep into it, you can simply, oh no, this is a 4 qubit situation. So you'll only have the mathematics available on up to 3 qubits, because it gets really heavy and it gets really difficult to watch the linear algebra after 3 qubits, although it's more or less the same thing, just in repeat. So by just watching the colors, the easiest way to solve it is add a single C gate. Yeah, and you can see why, because we have 2 greens, we add another red, 2 greens make a red, and they annihilate each other. Now, we have the first case in which we build an yin yang. What is an yin yang? As you can see, there is something quite special about it, and that's the fact that we have a 1 state, so we have a real part, a real number, 1 that has to become 0.5, 0.5. 0.5 real, 0.5 imaginary. To get that, we definitely need to add I. So I'm adding here an I. This is the matrix for the S-gate. Here we'll split, we'll have 2 states, 0.71, and then I'm adding another H-gate that goes and takes the 0.71s, make them 0.5. And as you can see, we have a negative with a blue and a green coming from this direction. This becomes gold because it passes through the channel from 1 to 1, and then we have the state we are looking for. Okay, now if we look here, we have 3 gates and we're supposed to flip, but we don't have an X. As the name entails, we need to remember how to do an X without an X. So that would be step 1. Why I put it on the left? Because it's quite obvious. If you watch where the superposition is, it's on the right. Why? Because on qubit 2, we have both 0 and 1 at the same time. On qubit 1, we have 1, 1. Yeah? So there has to be in the 1 state. So what needs to happen is the second qubit has to be in a superposition. So we can do this and we'll see just blue sigils, right? But by adding the complex imaginary part, the real number, we get the state we're looking for. Okay, now we want to get a plate from that. This requires some thinking. So let's see. If we annihilate it, then we have a single blue, but we also want to make it green. But that won't be enough. That would be a red. The 1-1 state. And if I add it, this will reverse it. So that's not a good solution. That's really interesting. Let's see. So what if then we can... No, if we split it again, that will not help. If we add an S gate here, this will just flip the sides. So what I'm thinking is, let's do this first. And the greens will go there. And if we double it, that would give us the middle green. And now we know that green with green in the middle will color everything the way we want it. So yeah, that's the way I think about the problem. First, I try to make sure that I get the directions straight, or at least I have first I make sure that I have the sigils, the amount of sigils I need, and then I'm thinking about the phase, and after thinking about the phase, I'm thinking about right. So how can we close the phases to make sure that they're in the right state? So this is how you come to the solution. It's an interesting puzzle, very short, but very interesting. Good. So I think we already solved this, we solved this. So do you remember 2s is a z? Yes, I do. But where? So on the leftmost and the rightmost qubits. So clearly we need to force these qubits in the 1 state. And we can achieve that by having knowledge of the fact that the 2 s's become a z, or just knowing green make red. By making red and going through a red channel, you get blue, so you get the flip right from 2s gates. And that's it.